Today, we're going to look at the second lecture of chapter number 8, and with it we basically finish chapter number 8, which talks about linear momentum, impulse, and collision. The learning goals for today: the first one, distinguish between elastic, inelastic, completely inelastic collisions. And then, of course, we'll solve problems in which bodies collide with each other. Now, when we talk about linear momentum here, and we try to define a collision for us here, collision is a strong interaction between bodies that last a relatively short time. So delta T is very short. And the assumption is that the interaction forces are much, much greater than internal forces, meaning that the system is isolated and the momentum is conserved. So that's how we look at collisions. Now, the type of collisions that we are going to encounter, the first one is elastic collision. The second one is inelastic collision. The third one, completely inelastic collision. So these are the types of collision that we're going to encounter. But you have to keep one thing in mind, that in all these types of collision, the linear momentum is conserved. So you have to keep that in mind. So what is different between these three different types of collision? And we'll start with the first one, which is elastic collisions. In elastic collisions, as in the previous slide, I told you in all these types of collision, the momentum is conserved. That means momentum initial and final is equal, or momentum 1 and 2, as we use in this book, is conserved. But in this type of collision, which we call elastic collision, the total kinetic energy of the system is the same before and after. And that's why we say here that K1 should equal to K2, meaning if you take delta K, and delta K here, it's not going to be K2 minus K1. It's going to be K1 minus K2. And if it's equal to 0, then we have this condition here, and we have a condition of what? Of elastic collision. So you basically seen in the last lecture when we talked about the gliders. So you have in this cartoon here A and B, and there is an spring. It's connected in the front of each. That would basically make the collision elastic. You can look at the VB1 and VA1 here, and you look at the vectors, the green vectors. Now they interact with each other, and since the springs are basically going to collide with each other, we're going to get elastic collision. And after the elastic collision, the two masses, they reverse direction, and you will get here VB2 and VA2 after the collision. The kinetic energy before and after, it's going to be the same. So in this case here, we're going to look at K1, which is equal to 1/2 mv VA1 squared plus 1/2 m, let's call it A here, B1 squared. That's your kinetic energy before. You look at the kinetic energy here, K2, which is 1/2 MAV 2A squared plus 1/2 MB B2 squared. And that's K2 here. Now we look at the difference. If the two are equal, that means you have elastic collision. If they're not equal, that means you lost energy. So the idea here is I look at my initial kinetic energy, and that's why we took the difference, K1 minus K2. I want to see if I lost energy or I didn't. Now, this system here, isolated system, so you cannot add energy in it. You may take energy out of it. So that's why the kinetic energy before, either it's going to be bigger or equal. And that's why we took K1 minus K2, just to see what the difference is. So in this case, when the kinetic energy or the total kinetic energy before and after is the same, then we have a condition of elastic collision. Now you can see something striking the floor here, and it gets back to the same height, meaning that if you have a potential energy here, it will get to the floor. That will all convert to kinetic energy, and that, of course, will bring it back. So the energy is basically conserved here. Now, in elastic collisions, you have two gliders, as the example for A and B, but you don't see springs here. So the collision is not going to be elastic collision. And after the collision, well, each mass will go in a different direction. Now, in this type of collision, as we said, momentum before and after is the same. It's equivalent to saying initial is equal to final, or B final is equal to B initial. So you can see all these different tones. So this holds in this type. But when it comes, we look at K2 minus K1. If K2 minus K1 is equal to 0, then you really have elastic collision. But in elastic collision, this is not going to equal to 0. And this means that you lost energy. And here we say that the total kinetic energy after the collision is less than before the collision. And in that case, you have what? You have a case of inelastic collision. You have something here that comes down, it hits, it goes back to a different level. You know that you're losing what? You're losing energy. And this is what we call inelastic collision. Now, there is a type where we say completely inelastic collision. And in this type, the momentum before and after is conserved. And of course, your energy, you have energy loss. That means the kinetic after is less than the kinetic before. But why we call it completely elastic collision is after the collision, the two bodies that are colliding, they stick and move as one object. So when we do conservation of momentum, it is MAVA1 plus MBVB1, and that's the momentum before the collision. After the collision, I have only one mass, which is the combined mass, MA plus MB, and of course I have one velocity for the combined two objects. So that's the difference. So when we give you a collision and I ask you, is this collision elastic or inelastic? Well, momentum is conserved, but you look at the kinetic energy before and after. If the kinetic energy before and after is the same, then you have elastic collision. If the kinetic energy after the collision is less than the kinetic energy before, then you actually have some energy lost, and this type of collision inelastic collision. But when I told you that the two objects stick together, move as one, then you have completely inelastic collision. So in elastic collisions, you lose energy. So for example, we have an image here where you have a car basically collided with something, and we say here that cars are intended to have inelastic collision so that the car absorbs as much energy as possible to protect you. So in collision with cars, we want the type of collision to be inelastic collision. So the energy is absorbed by the body of the colliding cars. Is this clear? Any question on the three types of collisions? Let's take a few examples here to illustrate these points. And this example here, we're going to look at a case of completely inelastic collision. we will consider the same example that we saw in lecture 1, where two gliders collide, but this time we assume that they stick together after the collision. So it's completely inelastic collision. A, find the common velocity, final x velocity after the collision, and find the energy lost during the collision, meaning comparing the initial and the final kinetic energies. In our case, we always say 1 and 2. So you have mass A here, with the mass is equal to 0.5 kilograms, moving to the right with a velocity of 2 meters per second. Another block with mass 0.3 kilograms, moving to the left with a velocity of minus 2 meters per second. They collide, and after they collide, they become as one mass. And here we say it's moving to the right because we're guessing that mass 1 has 0.5 kilograms, and maybe the speeds are the same. But this will come after we solve the problem. We'll try to find out which way it will go. So usually what you do is you look at the input. Before, MA is 0.5 kilograms, MB 0.3 kilograms. VA1x, it's equal to 2 meters per second. You're only looking at one-dimensional collision here along the x-axis. And VB1x is equal to minus 2 meters per second because it's moving to the left. After the collision, the two objects combine, and we're going to use a symbol C for it, and we say that MC is equal to 0.5 plus 0.3 is equal to 0.8 kilograms. And we want to look at the final velocity, and here we say it's VC2x. You don't see VC1x because before the collision, the two bodies were separate. But using 2 here because that's after the collision. Now we're going to look at conservation of momentum. So it is the P2x equals P1x here. And we're going to look at momentum after, which is MC VC2x equals MAVA1x plus MBVB1x. Now the MC is 0.8, VC2x is what we want to find. 0.5 times 2, that's for the momentum of A before the mass A before the collision. And 0.3 times minus 2, that's the momentum of mass B before the collision. Now 0.5 times 2 will give you 1, and 0.3 times minus 2 will give you minus 0.6. So 1 minus 0.6, that basically will give you 0.4. So your VC2x will be 0.4 divided by 0.8, and that will give you 0.5 meters per second. So the VC2x here came as positive value. That means it's going to move to the right with 0.5 meters per second. So, and that's why in the figure here we put the arrow pointing to the right, but actually this is where we confirm this. So usually you do the conservation of momentum to know also as well which way your combined object will move. Now in part B, they ask us about the energy lost. So we look at K1 minus K2. K1 is 1/2 MAVA1 x squared plus 1/2 MBVB1 x squared minus K2. And K2 here is 1/2 MCVC2x squared. So it's a half, and MA is 1/2, 0.5, so we write it here as a half. The VA1 c squared here, it's equal to 2 squared plus 1/2 times 0.3 times minus 2 squared minus 1/2 0.8 for MC, and our mass is VC2x is 0.5, so we write it here as a half, and of course you want to square that. This will give you 1 plus 0.6 minus 0.1, and it gives you 1.5 joules. So we lost this energy in the collision. So if the two masses they don't combine and move as one, we do not have a case of completely inelastic. We have a case of inelastic collision. And we will look at the kinetic energy before and after. If it's the same, you have elastic collision. If it's not the same, then you have what? You have a case of inelastic collision. Is this clear? Any question on this? Now, in this example here, we're looking also at another type of completely inelastic collision, but used in a practical way. This is what's known as the elastic pendulum, a simple system for measuring the speed of a bullet of mass mb, and we use b here to indicate bullet, makes a completely inelastic collision with a block of wood of mass, and we use subscript W here to denote it's the mass of the wooden block, which is suspended like a pendulum. After the impact, the block swings up to a maximum height y. In terms of y, mb and mw, what is the initial speed v1 of the bullet? So in the initial situation here, you have a wooden block which is stationary, and you have a bullet coming in with speed v1. When the bullet strikes the wooden block, it actually gets stuck inside the wooden block, and of course that will make the wooden block with the bullet move as one system. So that's our second situation here. It will swing to a maximum height here, which we call y. Now, you know, at this location here, if we choose this point here as equal to 0, and we'll use 2 here because we are taken at the second situation when the bullet is inside the wooden block and they're moving. So we can use y2 here as equal to 0. So that will basically your maximum height here. And you know, at the maximum height, we call it y3, if you like. And of course, at this height, the velocity will be what will be 0. You're only going to have a potential energy, and you're not going to have kinetic energy. They ask us to find out the speed. So we can look before the collision. The bullet has a mass mb. You can always measure that. And it has a velocity which is vb1x. The wooden block has mass mw, and the vw1x is equal to 0 because it's stationary. After the collision, now the combined mass of the bullet and the wooden block will be mb plus mw, and the v2x now, it's a common, it's basically for both of them. Now, I'm going to look at my conservation of energy, and I'm going to compare situation 2 to situation 3. Situation 2 is when the bullet inside the wooden block and the pendulum now swings, and it will go to this maximum height. So I'm comparing energy at 3 to the energy at 2. Now at 2, my y2 is equal to 0 because I set this equal to 0. And my v2 will equal to the v2x, which is the velocity of the wooden block and the bullet, and I can get this from the conservation of momentum. Y3 is equal to Y, which is the maximum height, and V3 will equal to 0. So if I look at my conservation of energy, it will be kinetic 3 plus the potential 3, and here it's a gravitational potential, equal to kinetic 2 plus potential 2. Now, my kinetic 3 is equal to 0 because my V3 here is equal to 0. My potential at 3 will equal to mgy, because here y3 is equal to y, which is the maximum height. Now, my kinetic 2 will equal to 1/2 m, and m here is going to be the combined mass of the wooden block plus the bullet, v2x squared. So I can cancel the m from both sides. I can multiply this by 2 to eliminate this. So the v2x will equal to square root of 2gy. So that should be my v2x. Now, the only thing that I can measure out of this experiment is y. But I want to know, and that will give me the v2x. But I want to know the vb1x. Well, if I look at my conservation of momentum, and now I'm going to compare 1 and 2 for the momentum. So I will say P2x should equal to P1x. And the P2x here would equal M, which is the combined mass of the wooden block and the bullet, V2x. That should equal to the mass of the bullet, that means the momentum before, times the VB1x plus MW VW1x. But the block is stationary, so this goes to 0. So what you have here, you will have M is equal to V2x will equal to MB VB1x. So out of this equation here, you can say that the V2x should equal to MB over M VB1x. And this is what I'm interested in. So now I'm interested in VB1x. So the VB1x here will equal to M over MB multiplied by V2x. And this is what you have here. M, which is MB plus M of the wooden block, divided by MB, and multiplied by the square root of 2gy. So with this simple experiment, if you just measure the maximum height the wooden block can achieve, you can basically figure out the initial speed of your bullets. That's a practical way of doing that. Is this clear? Any question on this? So we use here conservation of total mechanical energy, and we also use conservation of momentum to basically figure out the speed of a bullet. Is this clear? Any question on this? Now, let's look at elastic collision here. And in the elastic collision, you have two bodies colliding, that's A and B, that's VA1, that's VB1, and after the collision you will have VB2, and here you have VA2. Now in elastic collisions we said that, and in this case it's only one-dimensional, linear, meaning along the x-axis. So the momentum is conserved here, meaning P1x should equal to P2x. So what you have here, you have MA VA1x plus MB VB1x should equal to MA VA2x plus MB VB2x. Now you have elastic collision. So your kinetic energy K1 should equal to K2. So you have here 1/2 MA VA 1x squared plus 1/2 MB VB 1x squared equals 1/2 MA VA 2x squared plus 1/2 MB VB 2 VB 2x squared. And that basically gives you your conservation of total mechanical energy before and after. Now, between these two equations, and you can study this in your book or you can work it out, I can leave it to you to do that, you will find out a third relation, which we call relative velocity equation, and we always use that when we have elastic collision in one dimension. You will have VA1x minus VB1x equals minus VA2x minus VB2x. And that's a third relation, which we call the relative velocity equation. That's in the case of elastic collision. Now, we'll look at some special cases here. If you have a collision or head-on collision, meaning it's an elastic collision here, and the two masses are equal, well, the two particles after the collision, they will exchange their velocities. That means A with V1AX and B here, which is the same mass after the collision, and B here, it's, if you can say here, VB1X should equal to 0 because it's stationary. Now here, after the collision, the VA2X will equal to 0, and the VB here would equal the V1AX. What happens if mass A is much, much bigger than mass B? Whenever you see the less than, but you double that, that means much, much less. If MA is much, much less than MB, and that's the situation here, that's your A and that's your B, and of course this is the VA1X, and VB1X will equal to 0. When you have the collision here, MA reverses with VA2X equal to minus VA1X, and MB remains at rest. It's not affected. So that's the situation that you have here. Now, in the case when MA is much, much bigger than MB, and the B now is a stationary, well, MA will be unaltered, it will continue, and MB rebounds with about twice the speed of MA. So that's your situation here. The second situation here, it will be start moving with its own velocity as before, and this one will basically rebound back with VB2X. So these are special cases. So let's deal with an example here where we deal with elastic collision. We repeat the example of the two colliding gliders, but now we add to them an ideal spring bumpers so that the collision is elastic. What are the final velocities of the gliders? So we added here, it's the same situation, 0.5, 0.3, that's 2, that's -2, but we're adding springs here, and that will basically give us elastic collision. So initially, we have these two masses. V1AX is equal to 2, moving to the right. VB1X is equal to -2, moving to the left. And they ask us to find the VA2X and the VB2X. Now, I know two conditions here. I know that momentum should be conserved, meaning P1X should equal to P2X. So MAVA 1x plus MBVB 1x should equal to MAVA 2x plus MBVB 2x. Now MA is 0.5, VA 2x is 2, so 0.5 times 2, 0.3 times minus 2 should equal to 0.5 VA2x plus 0.3 VA2x. Now 0.5 times 2 will give you 1, and 0.3 times minus 2 will give you minus 0.6. That's why you have 1 minus 0.6, and it will give you 0.4 here. And what you will have 0.5 VA2x plus 0.3 VB2x is equal to 0.4. So I have two unknowns now in this equation. I need another equation. If you have two unknowns, you need two equations. Now you have two options here. You can use the conservation of total mechanical energy, but you will be dealing with V squared. Or you can basically use the relative velocity condition that we derived. And that's where it's useful now. So you'll have VA1x minus VB1x equals minus VA2x minus VB2x. Now the V1AX is 2 minus the VB1x is minus, so you get minus minus, that will give you 4. And here you'll have minus VA2x plus VB2x. So now you have here a second, you have an equation. From this equation here, since we use 2 here, you can take this to the other side. So the VA2x will equal to VB2x minus 4. Because you can take this to the other side, but you multiply with a minus, so you're actually getting the VA2x is equal to VB2x. And we call this 2 here. I can substitute 2 into 1 for VA2x. So I have 0.5. And for VA2x, I will have VB2x minus 4 plus 0.3 VB2x and equal to 0.4. Now 0.5 VB2x minus 2, because 0.5 times 4 will give you minus 2. Plus 0.3 VB2x is equal to 0.4. You can take this to the other side with a plus sign. You can add these two together. So you get 0.8 VB2x will equal to 0.4 plus 2. So, and this, of course, will give you 2.4. So your VB2x will equal to 2.4 divided by 0.8, and that will give you 3 meters per second. So now you have your VB2x. You can basically go to this equation here, and you have the A2x is equal to VB2x minus 4, and the VB2x is equal to 3, so 3 minus 4, and it gives you minus 1 meters per second. And that's how you obtain the final velocities here. Is this clear? Is this clear? Any question on this? So that's a case when we look at head-on collision or elastic collision. So usually you look at the conditions. Okay, if I give you a collision and I ask you, is it elastic or inelastic? Momentum is always conserved, but you look at the kinetic before and after. If they're equal, you have elastic collision. If they're not equal, you have an elastic collision. If the two bodies stick, you know right away it is completely an elastic type of collision. Is this clear? Let's take a few questions here, probably to illustrate some points and test our understanding. A boy of mass 45 kilogram runs at speed v. He jumps onto a 30 kilogram cart initially at rest as shown in the figure. If the speed of the cart with the boy on it is 3 meters per second. What is the initial speed of the buoy? So initially, you have a buoy, mass 45 kg, and VB1X, and symbol B here, we use subscript to denote the buoy, is V, and we want to find out what is the speed. And the cart has a mass of 30 kilograms, and VC1X is equal to 0 because it's stationary. After, the buoy jumps on the cart, well, the total mass of the cart will be the mass of the buoy plus the mass of the cart, which is 75 kilograms. And they tell us that the cart now moving with a common velocity, which is V2x, is equal to 3 meters per second. Now, I know that the momentum here should be conserved, so B1x should equal to P2x. So mass of the buoy, VB1x plus MCVC1x should equal to the total mass, V2x. Now, I know that VC1x, which is the initial velocity of the cart, is stationary, so that will give me 0. The mass of the buoy is 45. I want to figure out this. I will call it V here, which is the VB1x, should equal to 75 multiplied by 3. So if you divide that, okay, you will get V equals 5 meters per second. And this is now the initial speed of the buoy. Is this clear? So that's another way of how to look at things like this and use your knowledge of conservation of momentum to figure out speeds and so on. Is this clear? This final question here, I just want to take you back to what we did in the previous lecture when we talked about impulse. And in this situation here, a ball of mass 0.5 kilogram is initially moving to the left at 30 meters per second. After hitting the wall, the ball is moving to the right at 20 meters per second. What is the impulse of the net force on the ball during its collision with the wall? So you have 0.4 kilograms moving to the left, minus 30 meters per second. Then it rebounds back with 20 meters per second. And they ask us about the impulse. We talked about the impulse. That's one-dimensional motion here. So the Jx should equal to delta Px. That means it's P2x minus P1x. Your P1x here should equal to the mass, which is 0.4 times minus 30. And the P2x here should equal to 0.4 times 20. So your delta Px here should equal to 0.4 times 20, because you're taking 2 minus 1, minus 30, and this will give you 50 here, and that will give you 20 kilogram meters per second. So your impulse here will equal to, and it came as positive value, so it is basically 20 kilogram meter per second to the right. Of course, if you know the time the ball spends in contact with the wall, you can basically figure out the average force exerted by the wall on the because you know that Jx should equal to Fx times, but it's average here. We can put a sample times delta t. If you know the delta t, that you can figure out your average force. This is just to take you back to what we did in the previous lecture. So in this chapter, basically, any question on this one, you can send me if you have any question. Now, so in this chapter in general, we talked about linear momentum. And we defined linear momentum as mv. And then we talked about impulse. And we said that J should equal to the integral of the summation of the force delta T. And then we talked about conservation of momentum. We said P1 should equal to P2. And this is what we have when we have collisions. So we assume the collision that the time or duration is very short and the interaction forces are much, much greater than external forces. So we consider it as an isolated system. And we talked about, in this lecture, about three types: elastic, inelastic, completely inelastic. In all these three cases, your momentum is conserved. You may actually see in different books where they say initial should equal to final, or they may actually also say that final should equal to initial. In elastic collision, you add to it a condition where we say that K1 should equal to K2, meaning kinetic before equals kinetic after. And we actually, for head-on collision in one dimension, we arrived at the relative velocity relation, which is VA1x minus VB1x should equal minus of VA2x minus VB2x. And that's in the case of elastic collision. In the case of inelastic collision, also you have energy lost, where it's K2 minus K1. Completely inelastic, you know that you have energy lost, but the two objects stick and move as one. Any questions on these? Any questions on these? All right, good.